Hello everyone. We will continue on the morning session. I start taking this problem in the previous session, as I told you, but this is really a very important problem. In this problem, he's giving you a function m3 dx square y square minus z square, and it's equal to f of x, y, and z, which describes a closed surface, maybe an ellipsoid or something like this. But as we can see from this equation, we have two axes with positive sign and one axe with negative sign. And he's telling you to analyze this surface in the cases if C is greater than or equal to 0, C is less than 0 or a negative sign, and when C is equal to 0. When this value is greater than or equal to 0, you still will have two axes positive and one of the axes with a negative sign. And this is going to form a hyperparaboloid of one sheet, and it is symmetric about the axe with negative sign. So this one will be symmetric about this. If we are talking about greater than or equal to 0, which stand for all the hyperparaboloid that increases in positive direction, which actually will form the space, taking out from this space a shape of this hyperparaboloid of one sheet. And this is the general case when C is greater than or equal to a certain number. So the number will govern the depths of this hyperparaboloid and how it increases. For example, if C equal 25, I will be talking about the hyperparaboloid only with 25. So you can see here, there is a circle, okay, inside it. So it's like, and this is 50. So if we move the camera nearer to this shape, you will find the shape of the hyperparaboloid of one sheet that we are familiar with. Okay, for C less than or equal to 0, this is going to be the shape of the solid. I believe Muhammad told me about this. But if I want to graph, for example, x squared plus y squared minus z squared equal positive 1, equal negative 1, for example. This is going to be the case for this hyperparaboloid of two sheets. This is x, y, and z. Look to the ABC, a squared, b squared, c squared. So it's all 1, which means I will go for z positive 1, and I will go for z add negative 1. And this is the shape of the hyperparaboloid of one sheet. If this value is divided by, let's say, positive 4, so this is going to be a negative 2 and a positive 2, and this is going to be a negative 2. So the area inside these two parabolas will start to increase. Once you decrease this area or this value, this is going to be decreased. So as long as you decrease this value, the shape that you will gain or see, it's going to be like this. So it is almost a cone. Taking in mind that's less than or equal to negative 1 means all what's inside is filled with the material. It's a solid one. This is the case when you look at Z, X, Y, and Z for a hyperparaboloid of two sheet, but less than 0, when you are away from it, you will have this shape, which is really very close to the shape of a cone. But if you consider this equation with C equal to negative 25, you will have the regular shape of a hyperparaboloid of two sheet. Of course, I will have C equal 25, so you will have Z equal 25, dividing on it, this is going to be 25, so 5 positive, 5 negative, and you will start the shape of your hyperparaboloid with two sheet. It's going to be on this way. When C equal to 0 in specific, you are talking about a specific cone, which is the main cone or the two cone reflected in each other, and this is going to be a unique case. This is the difference between having an equation less than or equal to 0, greater than or equal to 0. If I told you I have x squared plus y squared plus z squared greater than or equal, okay, to 1, which means you have all the space with you except the unit sphere which is around the origin. Are you with me? Right? If I have x squared over a squared, y squared over b squared, z squared over c squared, and is greater than or equal to 1, it means you have all the space with you except for an ellipsoid with radiuses a on x, b on y, c on z, and this is a hollow shape inside the space. Are you with me? If I change the sign from greater than or equal to less than or equal, so it will be a solid ellipsoid. If I have the equation x squared over a squared, y squared over b squared, z squared over c squared, which is a solid, all on the shape of an ellipsoid. If I have x squared over a squared, y squared over b squared, z squared over c squared equal 1, I will be talking about the outer circumference of this ellipsoid. Did this make sense? Okay, Shabab? Okay, perfect. Now I will talk about the parametric curves. And this is very important topic because discussing in any shape, in Cartesian in general, you will be stuck with the reality that you will have at least 3 variables, variables in x, variables in y, and variables in z. But if you change into parametric representation, you will decrease the number of variables. This is why we usually need parametric representation. I've answered this question for you, why we use parametric representation of functions. The answer is very, very simple. It provides more flexibility and control when describing curves and surfaces, especially in the cases where standard equations become complicated. And you have tried this before, and we will need it more in the future. Because if I'm working with a circle, it will be x squared plus y squared equal to 1. If you try to integrate this function, you will have y on one side equal the root of 1 minus x squared, which is very difficult to integrate. It's not that easy to deal with. On the other hand, if I change it to polar coordinates, x squared plus y squared, it's gonna be r squared. So if you are talking about a radius or a square root for both sides, you will be talking with r. Compare integrating r with respect to the r. On the other side, integrating root of 1 minus x squared with respect to the x, for example. This is a main key for using parametric representation. Here's exactly what I've said to you. Some curves like circles or spirals cannot be easily represented as functions in x and y. This is why we are talking about R3 or R2. What if you are having a function in x, y, and z, and you need to integrate or work with it? It's going to be much, much simpler to be on a parametric form. Okay? For example, a circle is x squared, y squared equal r squared. It's difficult to express as a single function, y equal to f of x. That's exactly what I told you about. But if it is represented parametrically, it's going to be x equal r cosine t, y equal r sine t, and t run from 0 up to 2 pi. The very nice thing about the x and y in parametric representation in this form, and this will help you to imagine how the parametric representation work, how the parametric coordinates works exactly in projecting something like a circle. Let's see. I will talk about an example, well, this example is specific, but let me use x squared plus y squared equal to 1, which is simply a unit circle. This is a unit circle. So the radius is equal to 1. So in x coordinate, x will equal to cosine t, and y will equal to sine of t. Let's see how it works exactly. This is the x-axis, y-axis. By the idea, this is very, very important. It will help you down the road to understand how the parametric representation of these functions work. Okay, I will start. I will start with t equal to 0. Let's try. Right? Cosine 0 will equal to 1. But sine 0 will equal to, so the first point on my circle is going to be 1. Okay, let me change. The lines will increase since you are increasing t till we reach pi over 2. If I try to substitute by pi over 2, see, cosine pi over 2 is going to be 0. The other guy will work. Sine pi over 2 is going to be 1. So, once more, you will have the radius of 1. The numbers will be falling between them. So, Muhammad, for a certain value on x1 and y1, it has certain angles at t. So, it's like projecting points near to each other with respect to the t changing. So, it will represent, these are the points. These are the points gathering all together, and this will complete your circle once you go for t belongs to starting from 0 up to 2 pi. This is very, very important in understanding. So the parametric representation of a circle, it can be done like r cosine t, y equal r sine t, and this is the shape of your unit circle exactly. In this example, it is simple. Okay, in this example, it is simple. It shows you how the t changes and how the points are put all together. In general, if I belongs to R be an interval and let F and G belongs to I, and it goes into the range by two continuous functions. So if I have something in x and y exactly like the circle, a function in x and y, I can say that there is an f of t and g of t, which is really happen, cosine t and sine t. So representing the x as a function in t, y as a function in t. This is in plan. If I'm talking by generalizing this rule, if I'm talking in three dimension, so I will have x, y, and z. If I succeeded in getting f a function instead of x, a function in t instead of y function in t, and so on, I will be working with this. The function is f is x, y, and z, which is going to be f of t, g of t, h of t. So instead of dealing with just only two functions, I will add another function, and this will reduce in a huge way the number of variables that you will be working with. Okay? This is the main or called the parametric curve in R3. For example, geometrically, cosine t and sine t, where t is greater than or equal to 0, less than or equal to 2 pi, this is going to represent a circle, as we saw just seconds ago. So t runs from 0 up to 2 pi, and this is going to be the shape of the circle. What's going to happen if I have sine 2 plus 2 cosine t in a similar manner? I will start working with the angles starting from 0 up to 2 pi or whatever with respect to my domain. Now I've restricted the domain from 0 up to pi. If you try to make a substitution from 0 to pi, it will add points in x, and y, which is each substitution. Are you with me? Then a shape is going to be like this. This is if you are working from 0 up to 2 pi, not to pi only. And this is going to be the shape if you are talking from just only from 0 to pi. Okay, it's going to be this shape. And if you change it to be from 0 to 1.5 pi, and then you change the equation, the upper equation, to be 5 cosine t plus 2 sine t. So it's an ellipse, but on the x-axis. Okay, so it's mainly the same criteria that we are working with. Okay, perfect. For this case, or for these cases, now I'm going to talk about this 3 dimension. If you look to the first problem, which is x, y, and z, 3t plus 2, 8t minus 1,
and t. T runs from negative infinity to positive infinity. Any ideas about this equation? You already had it previously in parametric representation. I believe in the previous lecture, I've said something about it. And also in chapter 8 in linear algebra, we talked about this. That's an equation, if you remember, of a straight line. That's an equation of a straight line in parametric form. So usually the equation of a straight line in parametric form, it goes with a point plus some arbitrary constant belongs to R times the vector that's in the direction of this straight line. And this is exactly what's happening here. So 3t, it's gonna be the x coordinate of the direction ratio of the vector of that line. 2 is the x coordinate of the point on that line, and so on. Even if you don't remember this, but if you try to insert t for some points from negative infinity to positive infinity, this is what's gonna be. See, it's gonna be a straight line. And if you remark, it's actually cutting the xy plane. So you have a part of this line under or beneath the by 1, and the other part is above by 1. Are you with me, Leila? Okay. For the other equation, which is cosine t sine t and t, what do you expect from this equation? It's like a circle. It's like a circle. But I've taken one of its sides and I'm going to raise it up to positive infinity, and I will take the other side and try also to move it beneath by 1 up to negative infinity in the z direction. So how it's gonna be? It's gonna be a spiral. Okay? This is gonna be the shape of a spiral. Can you see it? It's a spiral. Okay? That's cutting the by 1, as you can see, and then moving up. If you get this spiral and you try to put it all together once more in by 1, it will come up to a circle. Do you read me? Which is the equation of cosine t and sine t. Do you read what I'm saying? Okay. Which is more than perfect. See how it's going to be complicated to express this in x, y, and z, and how it is simpler in dealing with in the parametric representation. Please, if you need to speak to each other, please go out. Once more, a parametric or regular curve in space is represented geometrically by a line or related curve C drawn by the points. When t increases, C also is the curve oriented in the increasing direction, as we saw right now with the spiral issue. A parametric curve in space can be thought as a trajectory of a particle. This is exactly what we did while we were trying to do the circle. So once you start putting t equal to 0, you will find a point here. The other point with t equal to another theta, or when t changes, so it will project another point. It will project a third point, fourth point, fifth point, till you start having the shape of this circle. Okay. What's the parametric curve or a vector function? In functions in 3D, we can represent certain functions, those are shapes, but also it can go for functions in the x direction, y direction, and z direction in a similar manner. So if you have 2 dimensions and you are talking about a function in 2 dimensions, I can represent it parametrically to be f of x and y equal to, let's say, an f of t in I plus a g of t in j, for example, if I am talking about R2. If we are dealing with R3, I will have another part, let's say h of t, but with the k, which is the canonical basis for R2 or R3 or whatever. Now I'm dealing with a vector function. So for x and y, it's going to be f of t and g of t. For vectors, if I have r as a function, so it's going to be f of t in the direction of I g of t in the direction of g, if I'm talking about 2 dimension. In 3 dimension, it will be the same, but I will add h of t, so you will have h of t in the direction of k. This is how the functions work in 3 dimension and in parametric representation, which is a way similar in dealing with. Okay, perfect. So this is the canonical basis, as I told you, I, j, and k. For a vector function, it is continuous. You have limits, you have everything. Okay? So if a linear combination of elements, okay, this is already done, and this is for the general definition of a vector function. Okay, the domain of vector function, which is really important. How to get a domain of a function in parametric or parametrically represented. All I have to do is to get the intersection of the domains of the functions, which are f of t, g of t, and h of t. So I'm just getting the conditions that will satisfy either, if in 2 dimension, it will satisfy f of t and g of t. If it's in 3 dimension, I will have how many conditions? 3 conditions. So for example, I believe this example is gonna be very, very good. Look at this problem. Here I have r, which is a vector function, and represented in x direction, y direction, z direction by these functions. If you look to the first canonical vector, which is the direction of the actual, which is cosine t, which is an explicit function. It has no regulation on the domain. It runs from negative infinity up to positive infinity. But if I go for the y direction, if I go to the y direction, I'm just on the y direction. I will have log. This is going to be the first condition. It's going to be the log of 4 minus t. Yusuf. وبنسي طبعا. The log 4 minus t. Okay? The log 4 minus t. This is going to be a condition. What's the condition? 4 minus t must be greater than 0, which is going to lead to t must be less than 4. That's the first condition, which actually a condition for the second component to be working. In a similar manner, I will go for the third one. Okay? I will go for the other function, which is the root of t plus 1. Exactly the same. So I will go for the second condition, that the root of t plus 1, it has a regression that t plus 1 must be greater than or equal to 0, which means t must be greater than or equal to negative 1. If you remark that t now forced to be within the interval greater than or equal negative 1, but less than the value of 4 for this function to be represented. Okay? Once more, the function cosine t is defined in all real numbers, so it doesn't impose any restrictions. For the logarithmic part 4 minus t, the logarithmic function is only defined in the positive argument. So 4 minus t must be greater than 0. Exactly that's what happened here. I will try to get t in one side, so t must be less than 4. And I will take the third component, imposing the restriction, which is t must be greater than or equal to negative 1. So the domain simply will be the value in between greater than or equal to negative 1 and less than or equal, and less than 4. This is how to get the domain of this function. The next question, the limit of a vector space or the limit of a vector function. If I want to get a limit of a multi-variable function in parametric representation, I will have to take the limit to each one of these canonical bases. So, if you are taking a limit of t tends to t0, it means you will do this for the I part, for the j part, and for the k part. So I'm taking the limit and distributing it on the f of t, g of t, and the h of t components. And the results will represent the b vector value, standing for the value of this limit at the x and y and or at I and j and k. Are you with me? معايا محمد? Okay.
Next step. As long as you have limits and you have definition, what's the definition? If I want the definition of a vector function at certain point, what I have to do is to make the substitution. Take the function at this point and start substituting. معنى الكلام. لو أنا عايز أعرف function continuous ولا لا at certain point, what to do? What's the check? Do you remember? The value of the function equal the value of the limit. So first of all, the value of the function exists. Second, the value of the limit exists. Number three, third condition, they have to equal to each other. So it's exactly the same. But I will have to do this at the three components, the I and j and k. So the function definition, it means you will take the function in the form of f of t, g of t, h of t, and then make a substitution. So it will give you a point, keep it aside. And then I will take the limit of this function tending to the point that I want to discuss the continuity at. If you find the limit exactly the same, the value of the definition, so this function is continuous at this point. This is exactly what the definition. Why we are going through limits and continuity? Why? Because it's an introduction more than beautiful. It's an introduction for differentiability. So now I'm talking with functions. If I differentiate in parametric representation, I can get its slope, its rate of change, and which is the differentiability. Exactly what's going to be said. A vector function is continuous at a point in its domain, if I will be f. Each of its components is continuous at this point. I mean by these components, which is f of t, g of t, and h of t. Now, for a vector in parametric representation, we have the tip. As I told you, it's exactly like what we drew the circle from just seconds ago. In 3 dimension, this is going to be the t. In order to draw such a thing, it's going to be a point with an x, y, and z components at certain values of the t function. Okay, so this is the representation once more, and that's the derivative. So the derivative of a certain function in 3 dimension or a vector function is going to be the derivative of each component at I and j and k. So we do the derivative exactly the same. يبقى أنا بعمل الدerivative عند الcomponents بالظبط. As long as the limit that exists, this is why we took the limit and we took continuity in order to be able to have the derivatives from the definition. This is the definition of the derivative, which is r of t plus h minus r of t divided by h when h tends to 0. If this exists, you will have r dash, which is the derivative of u function. And it's already applied here, and for the higher order also it's exactly the same, so you will be very good. So also the derivative of a vector function is a vector function. It will develop another vector function. Okay, derivative rules. This is really, very important. It's exactly like the rules that we took previously in derivative. So, for example, if I have previously in differentiation, we know that differentiation can be distributed on sum or difference, okay, of certain functions. It's exactly the same. So if I have R1, a vector function, and R2, a vector function, and you are getting the derivative of these two functions, I will get the derivative of the first function plus the derivative of second function, plus or minus. If they are multiplied in each other, if f function of R1, and I want to get the derivative, it's going to be the derivative of f times r, and then vice versa. So it's the derivative of the first function times the second, plus the second function derivative times the first. Also, in the case of dot product, it will be the same result. And in cross multiplication, also will be the same result. So if I multiply cross product R1 as a vector and the R2 as a vector function, and getting the derivative of these two functions, what's going to happen? If I did that, I will have a cross multiplication with the derivative of the first vector function times the second, and then vice versa.
So it also goes for cross multiplication. Finally, for composite functions, which is the function inside the function. If I have R1 composite of alpha, R1 composite R2, all I have to do is to get the derivative of R1 first as a function in R2 times the derivative of R2. And that's the formula for doing this parametric or composite function representation or derivative. Okay, very well. These are some graphs explaining how we get the limit, which is f of x plus h minus f of x divided by h. But here we are dealing with vector functions. It's exactly the same. And also, this explains exactly like the single variable functions. When you get a substitution with f dash, you will get the slope or the tangent to your curve. So it's exactly the same. I believe all of this will be very nice to see how the questions are going to be on this part. So let's start with this question. List 4 curves and vector functions. Represent geometrically the following parametric curves in R2 and determine the velocity and acceleration vectors at each point. Why he asked me about velocity and acceleration? Because it is the direct application on the first derivative and the second derivative of this displacement function. The first function is 2t plus 1 and t squared. Once you try to graph this function, it will be projected as I told you, okay? And it will represent a second degree parabola on this shape. So if this is the case of 2t plus 1 and t squared, this is r, this is the main function. If I want to get its derivative, it's going to be really very easy to get the velocity or to get the acceleration of this function. So if I have x and y, which equal to 2t plus 1, okay, and t squared. Let's start, this is r. So in a vector direction, in a vector form, it's gonna be 2t plus 1 in I plus t squared in j. Okay, I need the velocity, so all I have to do is to get r dash. So the velocity is going to equal to r dash, which is going to be a 2 in the direction of I, plus a 2t in the direction of j. If I want to get the acceleration, so I will get the second derivative of this displacement, which is going to be 0 in the I direction, plus 2 in the j direction. And that's the shape of the acceleration that you will get from this function. Okay, here we go. This is first RT. I will get the first derivative, which is going to be 2 plus 2t. Similarly, like I will get the acceleration, which is 2j. For the other problem, which is sine t cosine t minus 3, it's a circle, but it has been shifted, a unit circle, but shifted by -3. So once you try to graph it, this is going to be the shape of your circle. This is the center at -3. So we already moved it 3 steps down, okay? And once more, this is r of t. If I want to get a velocity, all I have to do is to differentiate all the components, okay? Here we go. So differentiating sine t is going to be cosine t. Differentiating cosine t is going to be negative sine of t. And this is for the I direction and j direction. Similar manner, if I want to get r double dash, so all I have to do is to once more start differentiating. Cosine t is going to be negative sine t. And I have negative of a sine. Differentiating sine is going to be a cosine. So this is the acceleration and runs from t from 0 up to 2 pi. Now I have a vector function, first derivative and second derivative of this vector function. In a similar manner, here I'm talking about 3D, three dimension. So for the first one, it's a 2 sine t, 4 cosine t, and the t is 1. So you can think of this as having an ellipse, which is 2 sine, 4 cosine, an ellipse, and you come to one of its steps and you just move it just for one z unit. So it's gonna be like having an ellipse like this, and you just make it just with 1 unit in the z direction. And this is the shape of this function. This is the r function. If you want to get the velocity, it's going to be exactly the same. I will have to differentiate each component. So it's going to be a 2 cosine t minus 4 sine t, and this is going to be a 0k. If you're going to get the acceleration, exactly like what we said, so it's going to be negative 2 sine t minus 4 cosine t and a 0. And this is the shape actually. This is an ellipse with one of its steps is moving. And that's the shape if you are looking from a wave angle. Okay, for the second one, this is cosine t sine t, and you have t over 2 pi, and the t runs from 2 pi up to negative pi. And in a similar manner, this is r of t, this is the velocity, and that's the acceleration relative to this function. All I have to do is to differentiate each component for 1 time to get the velocity, 2 times to get the acceleration, and that's the shape of this spiral, which goes from the negative infinity up to positive infinity. Okay. Now compute the velocity and acceleration for all t and define the equation of the tangent line at the specified value of t. So now I need you to get the velocity and acceleration, and then to get the tangent equation of these surfaces. So for the first equation, which is sine 3t cosine 3t, and you have 2t to the power of 3 over 2 at t equal 1. Let's see how to do it. First of all, I can write this function as a vector function, which is very, very simple. As I told you, is r, here we go, r is going to equal to sine 3t in I direction plus a cosine 3t in the j direction plus 2 of t3 over 2 in the k direction. This is r, which represents the points. Then I will differentiate to get r dash, which is going to be the velocity.